Okay, so this video is going to cover the last little bit of chapter 4 and finish our discussion of atoms forming ions by either losing electrons, as in the case of cations, or gaining electrons, as in the case of anions. So to remind you, we have a cation when our atom is positively charged, which means, or it indicates we have more protons than electrons in our atom. So our atom has lost electrons. And an anion, we have more electrons than protons. So we have a negative charge, and that's when we gain electrons, so that we have more electrons than protons in our atom. And so the types of elements that are going to form cations are the ones on the left-hand side of the periodic table. They're the metals, okay? Because remember our periodic trends, they have a low ionization energy. Okay, so our anions are going to be the ones that are nonmetals that are on the right-hand side of the periodic table, and they have very large electron affinity. So let's look into more detail about different positions on the periodic table and how they form ions. So first we can talk about groups 1A through 3A, which are shown right here on the left-hand side of the periodic table. And actually, I'm going to change that. So group 3A is here. Okay. So this is, oops, this forms +3. Okay, so that's group 3A. All right, so group 1A and 2A are all metals, but if you recall, we have the area where metals and nonmetals the transition between metals and nonmetals. So we have this kind of stepped area here, right? So the things that are below in group 3A, those are metals, and those are going to form positively charged ions or cations, okay? So again, in groups 1, 2, and the metals in 3A, okay, you're going to be losing electrons, and the electron or the cation that you form is going to have the same electron configuration as the previous noble gas. So let's compare three different ions. So lithium is going to form a +1, okay, and beryllium, which is right next to it, is going to form a +2 ion, okay, and let's look for aluminum, okay, down here, and that's going to form a +3 ion, okay, and so let's consider which noble gas they are isoelectronic with. So isoelectronic, okay. So lithium, when it becomes a +1 ion, it means it loses 1 electron. So lithium is atomic number 3. So when it loses an electron, it's going to have 2 electrons, which is the same number as helium, the noble gas in the previous row has. Okay, the same with beryllium. So if beryllium has a +2 charge, okay, then that means it has lost 2 electrons. Okay, so beryllium is element number 4, and so it starts out with 4 electrons. When it loses 2 electrons, okay, that means it has 2 electrons left over, and again, that is the same number of electrons as helium has. Okay, so the beryllium +2 ion has the same number of electrons as helium. All right, so what about considering aluminum? Okay, so aluminum again is in group 3A. It's going to lose 3 electrons. Okay, so aluminum has an atomic number of 13. So an aluminum atom has 13 electrons. Okay, the Al +3 ion has 3 fewer electrons than that, so that will have 10 electrons. Which element has 10 electrons? That's atomic number 10 is neon. So aluminum 3+ ion is isoelectronic with neon. Okay. All right. So if we continue thinking about our cation formation, okay, we can talk about the neutral atom of magnesium, okay, which is in group 2A. And this is its electron configuration, or if we were writing magnesium in our noble gas notation, we would pick the noble gas that's in the row above it, neon, okay, and then we would find out which block it's in. This is the S block, okay, so it's going to have S electrons, and then which row it's in, 1, 2, 3, it's in the third row, so that's going to be 3s orbitals that those electrons in excess of neon are. So remember that neon has 10 electrons, magnesium has 12 electrons, okay, and so we know we have 3s orbitals, and we have 2 electrons in those because magnesium is in the second block or the second column of the S block. Okay, so this is how we would write it in noble gas notation. All right, so now these electrons here are in the highest energy orbital. Okay, so to get to a noble gas configuration, you would lose those electrons. Okay, and when you do that, okay, magnesium still has 12 protons in the nucleus, right? But the magnesium ion, okay, only has 10 electrons. Okay, so the net charge on the atom is going to be +2, right? So we've got 10 protons, so that's +10, and, oops, I'm sorry, not 10 protons in the nucleus, we have 12 protons in the nucleus. There we go, sorry. 12 protons. The ion, the magnesium ion, let's just say the magnesium ion, has 10 electrons. Electrons are negatively charged. Okay, so we've got 12 positive charges, 10 negative charges, so that leaves us with +2 is the net charge on the magnesium ion. Okay, so we would write it as Mg2+. Our convention is that we write the number first and then the sign of the ion later. Okay. Now, if we look at this, that has 10 electrons. Neon has 10 electrons. So again, we're going to be isoelectronic with neon, the noble gas, when we have a magnesium ion. Okay. All right. So if we want to look at groups 3A through 5A, so this is 3A, 4A, and 5A, if we're looking down the right-hand corner at our periodic table. Okay? And so remember that the things that are metals in these groups, I'm going to color blue here. Okay? So not all of these elements that are in those groups are considered metals. Okay? Just the ones that are below that kind of staircase line where we are defining our metals versus non-metals. And the things that are in green here are shown, are what we call the metalloids, and the things I'm coloring yellow are non-metals. Okay, so yellow is going to be non-metals. Okay, and our blue is going to be metals. And, oops, our green are our metalloids. So what I'm talking about on this slide, okay, is going to be the metals in groups 3A through 5A. Okay, so those things that are colored in blue are going to form cations. Okay, and so if you recall, okay, this right here is the P block. Okay, so the elements that are in the metals that are in this region have P electrons. So what they're going to do is they're going to lose their highest energy P electrons, and their goal is to form the same electron configuration as the last transition metal in group 2B. So the question is, where's group 2B? Right here. Okay. So that's group 2B. All right, so if we look at it, okay, if we want to consider tin, so let's show you where tin is on the periodic table. Okay, so it's Sn is tin. Okay, and so its electron configuration, if we're using that noble gas notation, right, we go up one, find the nearest noble gas that has this fewer electrons. So that's chromium. Krypton, sorry. So this is krypton. Okay, so we're starting with the krypton. And then we are in the P block, okay? But we're in 1, 2, 3, 4, 5. Okay, so we are going to have 5 P electrons. Okay, we are the second block in, so we're going to have 2 5p electrons. That's there. But then we also know that everything below that has to be filled. And so that's our 5s electrons. Okay, and if you recall, we have our 4d is also going to have to be filled. Okay, so krypton does not have d electron or 4d electrons. All right, so these electrons here, okay, are all of the electrons in excess of krypton. So they're the extra electrons that tin has that krypton doesn't have. So krypton is element 36 and tin is element 50. So krypton has 36 electrons and tin has 50 electrons. So if we add these up, okay, so 36 plus these 4, that gets us to 40, and these 10 here get us to 50. Okay, so this just shows the excess electrons beyond what krypton has. Okay. All right. So in this case, okay, the highest energy electron are going to be those in this 5p shell. Okay, and so we are going to lose those 2 electrons, and what we're going to have is so if we're starting with 50 electrons and we lose 2, okay, so if we lose 2, we're going to have 48 electrons. What is element 48? That happens to be cadmium. Okay, so cadmium has an atomic number of 48. So it's got 48 electrons. Okay, now remember, very important not to confuse losing electrons with losing protons, right? So when we have tin and we take 2 electrons away from it, what we're left with is still an atom of tin, right? Because it still has 50 protons in the nucleus. So still has 50 protons in the nucleus. Okay, but it only has 48 electrons, so it's got a net charge of +2. Okay, all right, and so this is what the electron configuration in noble gas notation would look like for the tin. What would you call it? The tin ion, cation. Okay, so it is going to wind up being isoelectronic with cadmium. It's going to have the same number of electrons as cadmium. Okay, so the Sn2+ ion is isoelectronic with cadmium. Okay, and so if you are over here on the right hand side and you're dealing with any of these metals over here, okay, they are going to lose electrons to become isoelectronic with one of these guys right here. Okay, so So if we're looking at lead over here, okay, it's going to lose 2 electrons to become isoelectronic with mercury. Okay, bismuth will lose 3 to become isoelectronic with mercury, and so forth. Okay. All right. Okay, so transition metals are a little more complicated again. So our transition metals are going to be these guys right here, okay, in the middle of the periodic table. And so these guys are going to lose electrons from their NS orbital first. And remember, when we're talking about N, we're talking about the row number that it's in. Okay, so this is the N. So they're going to lose S electrons first, okay, and then they're going to lose electrons from the N-1D sublevel, where N is their row number. Okay, so for example, let's look at cobalt. Okay, so let's find cobalt on the periodic table. Okay, so if we want to look at cobalt, it's right here. Okay, so remember, these guys right here are in our D block. Okay, and so if we look at cobalt, okay, the nearest noble gas is argon. Okay, so that's argon, and then we are in the 4th row. Okay, so they're going to have 4 S electrons, so it'll have the 4s2, both of those are going to be filled, and then we count over how many it's in the D block to see. So we're 1, 2, 3, 4, 5, 6, 7. So it's 7 spots over in the D block, so there's going to be 7 D electrons. Okay. So it turns out that cobalt can form 2 different ions. It can form what we would call a cobalt 2+. So if it forms cobalt 2+, it loses those 2 electrons that I just highlighted. Okay, so that's cobalt 2+. The other ion it can form, okay, is cobalt 3+. So to do that, it's going to have to lose 1 more electron. Okay, and that electron that it's going to lose, okay, is going to be 1 in the in the D orbitals. Okay, so what's going to happen is if we have cobalt 3+, its electron configuration, okay, is going to be 3d6, and then it's not going to have any in the 4s. Okay, so the s's get lost first. Okay, so the cobalt 2+ electron configuration would be 3d7. Okay, so there's not going to be any 4s electrons at all in either case. All right, so we talked about ionization energy before, and if you recall, okay, ionization energy is the amount of energy it takes to remove an electron. From an atom. So the easier it's going to be, the lower that amount of energy is going to be. All right, so what we call the second ionization energy, okay, or IE2, okay, is how much energy is required to remove a second electron. Okay, so in the case of the sodium ion, okay, so remember sodium is in group 1A, so this kind of ion right here, the Na+1 ion, is what you're used to, what will normally happen. Okay, so, and it takes 496 kilojoules per mole to remove this electron here. Okay, so if I put in this amount of energy, okay, I can pull that electron out of that 3s orbital and send it to some other atom. Okay, now If I then think about, if I'm starting with a sodium ion, what I'm interested in is taking away one of these electrons, okay, in this nicely completely filled 2p orbitals, okay, it's going to take a whole lot more energy to do that. Okay, so we would be taking away this electron, and to do that, it would take 10 times, actually, yeah, 10 times more energy practically, okay, so So the more electrons you take off, the harder it is going to be to remove those electrons often. And if we think about where these electrons are with respect to the nucleus. Okay, these 2p electrons are closer to the nucleus, right? And so they're going to have a higher force of attraction based on Coulomb's law than this guy right here who's further away from the nucleus. So it makes sense based on what we know about the attraction between the nucleus and the electrons that those that are farthest apart are easiest to take off. Okay. All right. So let's just look at magnesium, right? So if we're looking at our electron configuration for magnesium, it's got 12 electrons. Okay, so we are going to have electrons in the 3s2 level. Okay, and so remember we said that magnesium is in group 2a. So magnesium loses 2 electrons to form an Mg2+ ion. Okay, and so if we look at this table here, this is the, again, amount of energy required. So this is to pull an electron from a neutral atom. All right. And then this one is if I'm starting with a magnesium cation, but it only has lost 1 electron, it requires about twice as much energy. Okay, so 2 times the energy. And we said that, that these electrons are the ones that are going to leave so that it can get to a nice, noble gas electron configuration. And so if we tried to pull one of these guys off, this would be trying to take one of those 2p6 electrons off. Then, again, we have a much bigger increase in energy that's required, right? So, if we compare it to the second ionization energy, it's maybe about 4 or 5 times. All right, but if we compare it to that first electron, taking that first electron off, right, it's 10 times the energy. All right, so again, main point, the more electrons you take off, the harder it is, right? So let's write it here, bottom line, and let's make it a real bottom line, and I'm going to move it all the way to the bottom here. So bottom line, the more electrons you remove, the harder it gets. All right, and so that's what you should remember. All right, so now let's spend just a minute or two thinking about atoms that form anions. So, all right, so these are ones that are going to gain electrons, right? So anion formation, gaining electrons. Okay, so chlorine is in group 7a. It's a halogen. And that is going to lose an electron to form what we call the chloride ion. So start getting used to seeing when we have anions using this IDE suffix, okay? Because that is the naming convention we use for anions, okay? Naming convention for anions, okay? So we would say something like a sodium ion for a cation, a positively charged ion. But for a negatively charged ion, we add IDE to the name of the element, and so it becomes the chloride ion. All right, so if we look at the electron configuration of chlorine, what we have is here we have our 3p subshell, and it is almost all filled. It's just not quite filled. And so we could get to a nice stable electron configuration and have a noble gas electron configuration. So if we look at the periodic table, I'm going to draw just quickly. We've got helium, and then we've got neon. And these are our halogens. So we got fluorine, there's chlorine, and there's argon. Okay. So helium is 2, neon is 10, argon is 18, and chlorine has 17 electrons and fluorine has 9. Okay, so the easiest way to get to a noble gas configuration is to, again, just put one electron, get an electron from somewhere, okay, and put it in that last 3p orbital, okay. And so this is going to be at the heart of some of our chemical reactivity that we see, right? So we have things like elements in group 1A that are energetically favored to give up an electron to get to the next noble gas. And then there are elements in group 7A, like the halogens, like right here, where if they gain an electron, they will get to this stable noble gas notation. So chlorine, okay, so the chloride ion is going to be isoelectronic with argon. And again, so you're going to find that elements that gain electrons to get stable are going to react with elements that lose electrons to get stable. So things like the alkali metals, lithium, sodium, potassium, are going to react with halogens, fluorine, chlorine, bromine. All right. Okay, so let's talk about sulfur for a minute. So sulfur is in group 6A. Okay, so if we're looking at our periodic table here, it's one more in from the halogens. Okay, so this is 7A, this is 6A, that's group 8A. So this is noble gas. There's our halogen. And then these are called the chalcogens. It's one of our named groups that we don't use that name that much. But so we've got the fluorine and chlorine and the neon and the argon that we talked about, right? And there's helium up there. So group 6A has oxygen, and sulfur is right here. It's one to the left of chlorine, okay? So sulfur has 16 electrons, right? And so if we look at sulfur, it has one less than chlorine, so it's got 2 unpaired p electrons. And so again, if it can react with something that can give up 2 electrons, it can have a filled p orbital, and it can become isoelectronic, okay, with the nearest noble gas. So if we're going up by adding, protons to the nucleus and electrons in a neutral atom, if we go over 2, argon is that nearest noble gas, okay? So when we talk about the S2 minus, the sulfide ion, okay, so this is the sulfide ion. We would say it is isoelectronic with the argon atom. Okay, its electron configuration, okay, which when we're starting out, okay, is neon plus 6 electrons, right? Or I'm sorry, yeah, neon plus 6 electrons, and when we pick up 2 electrons, it's neon plus 8 electrons. All right. All right. Let's talk about some exceptions just briefly before we're done. Okay. So we've been talking about group 1A, group 2A, and group 3A, the metals. So those are the things in blue. And they lose 1, 2, or 3 electrons to form cations. Okay. And the easy way to remember this is the charge on the cation is equal to the group number, right? So we get +1, +2, and then these guys down here form +3 ions. Okay. All right, so now if we're talking about the nonmetals, so our nonmetals that are in groups 7A, 6A, and 5A, okay, they're going to gain electrons, and so they will form negatively charged ions. So we'll have -3, -2, -1. Okay. And again, this is just going to refer to the nonmetals that are in that group. All right, so the charge on the ion is going to be equal to 8 minus the group number. So this is the absolute value. Okay, so if we have group 7A, right, so the charge is going to be 8 minus 7, which is 1. But then we have to put a negative sign. So I actually don't think this is all that helpful. I think it's easier to just remember, how far do I have to go to get to 8 electrons, right, in your valence shell? Do I need 1? Do I need 2? Do I need 3? How many boxes over do I have to go? All right. So up to this point, we have not talked about these guys right here in group 4A. Okay, and that's because they don't form ions. Okay, so ion formation for these is really uncommon. And when we talk about bond formation, instead of taking up electrons or giving them, these elements, okay, tend to share electrons. So share instead of gaining or losing. And that's what we call covalent bonds. All right. And the reason, again, being is that, remember, every electron that you lose or every electron that you gain requires a whole lot of energy. So 4 electrons is the tipping point. Okay, we just don't do it. All right, so we've got some electron configurations to use for practice. Okay, so let's try to do some of these. Oops. Okay. All right, so let's talk about potassium. All right, so potassium is our first example. Potassium is over here on this position in the periodic table, right? And so if we're using our noble gas notation, the nearest noble gas is argon, right? And then we know we're in the S block, we're in the 4th row, and we're in the first box. So we go, 4s1. That is the neutral atom. Okay. So to make an ion, okay, it's in group 1, and we know it forms a +1 ion. Okay. And so that would be, we would take this electron here away, and that would just leave us with the argon configuration. Okay. All right. And so that, let's think about how many electrons that would be. So we have 19 electrons in the neutral atom. In the potassium ion, we would have 18 electrons. And so our electron configuration in SPDF notation for the potassium ion is going to be 1s2, 2s2, 2p6, 3s2, 3p6. Okay? And let's check. We have 6, 8, 14, 16, 18. That's 18 electrons. Okay. All right. So our next example is going to be the titanium ion. So let's look at where titanium is on the periodic table. All right. So, so titanium is, I'm having trouble seeing my thing here. Why can't I find titanium? Because it's over here. There we go. All right. So let's do the electron configuration for titanium, the titanium ion. Okay. So titanium, the neutral atom, is going to be argon. Okay. And this is in our D block. So, and it's in the 4th row. So it's going to have 4s2. Whoops, that should not be an equal sign. Sorry. 4s2, and then 3d, and it's the second one in 2. Okay. So to get to a noble gas configuration, okay, the way we would go is we would remove all these electrons. Okay, so that's going to give us a titanium, 4+ ion, which is going to be isoelectronic with argon. Okay, and again, the electron configuration for argon is this right up here, the same as for the potassium ion. Okay. All right. So now let's talk about bismuth. Okay. So bismuth is going to be down here on the periodic table. It is a metal that's in group 5A. So remember that this one is going to lose electrons to get to the electron configuration of mercury. So to do that, because that's the closest element that is in group 2B here. Okay. All right. So we would go 1, 2, 3. We'd have to lose 3 electrons. So bismuth becomes bismuth 3+. Right? And so what is the nearest noble gas? The nearest noble gas is xenon. Okay. And now it's going, the neutral atom, okay, so bismuth neutral is going to be xenon. But we're in this is the P block here that bismuth is in, right? And it is in the 6th row. So we're going to be 6. And then it's going to have, it's going to have, let's see, 1, 2, 3 in its P block. In its P orbitals. I'm going to use, 6p3. Okay, and then everything before that has to be filled. Okay, so that would be 4f14, and 5d10, and then 6s2. And so these are, this one's a difficult electron configuration because there's a lot of electrons beyond what you see in the nearest noble gas, okay? But having this electron configuration makes it a little bit easier to see how we wind up with a 3+ ion, because if we just lose these 3 unpaired electrons, then everybody else is paired, okay? So our electron configuration for Bi 3+, okay, is going to be xenon 4f14 5d10 6s2. Okay. All right. All right. So sulfide ion. Did we do sulfide on previous page? I think we did. Yes, we did. So we're not going to do sulfide again. We're just going to say, see the previous slide. All right. Okay, so, and we're going to save talking about iron for when we in chapter 5, because iron is one of those ones like cobalt where you can form differently charged ions. Okay. All right, so let's finish by talking about ion size. Okay. Your ion, in terms of its size, is going to be related to the size of the atom from which it came, okay, as well as the charge, okay. So the key trend, okay, cations, since you're taking an electron away, are smaller than their neutral atoms, okay. Neutral atoms. And then anions are going to be larger. Okay, so anions are larger because you're adding electrons to them. So it's easy to reason that out, because if you're taking something away, your thing gets smaller. If you're adding something to it, it gets bigger. Okay, and anions, again, generally tend to be larger than cations, because of a little extra electron-electron repulsion. And then all the other, the regular periodic trends apply in terms of as you go down a group, as you go left to right. Trends apply for size, okay? All right, so I've been using the term isoelectronic, so I just want to further clarify what we mean when we say that. Okay, so we've got the same number of electrons, but different numbers of protons. Okay, so here we have 4 different species. When I'm a chemist and I'm using the term species, okay, what I mean is that I mean a thing, a molecular or atomic thing. So here we go. We have 4 different things, okay, and they all have the same number of electrons, okay, but we have 4 different elements, right, because they each have a different number of protons. And remember that proton defines what our element is, okay? All right, so if we look at this, okay, all of these things have the same number of electrons, okay, but remember that the charge on the nucleus is going to be different, right? The charge on the nucleus differs, right? It gets more and more and more positive as we're going down here, okay? So positive charges attract our electrons, right? So if we look at the radius, if we look at the size, right, we get smaller, okay? And as we go down, right, we have more protons, more positive charge, more attraction, a stronger force of attraction to those electrons, right? So they're pulled closer, and so that means your size is smaller, okay? So isoelectronic ions, okay, are not all the same size, and that's because the nucleus is different. And the nucleus of an oxygen ion or an oxide ion is going to be is going to have a stronger attraction for the weaker attraction, sorry, for those electrons that are farthest away than a magnesium ion, because magnesium has more positive charge in the nucleus. And just to remind you, that's Coulomb's law, right? So if this is let's say this is the nuclear charge, and this is our electron, okay? So if this number gets bigger, this number is going to get bigger. And this is the force of attraction that the protons in the nucleus have for the electrons. That's the context in which we're using this equation, okay? All right. So let's finish by summarizing our periodic trends, okay? All right, so our periodic trends, as we go down a group, okay, then our orbital energy is going to increase, because, we talked about why. So as we go down a group, our orbital energy is going to increase, because we're getting more and more electrons, so we have more and more shells, okay? Our effective nuclear charge is going to decrease because we have more of those inner electrons, which means our atomic radii is going to increase, because if you have a low effective nuclear charge, the electrons that are farthest out can have less of an attraction to the nucleus. Our ionization energy is going to decrease. It's going to be easier to lose electrons, and our electron affinity is going to decrease as well. These two kind of go in concert with one another. All right, so that's down a group. Across a period, left to right, orbital energy is going to decrease because your effective nuclear charge is increasing and you have more of an attraction to the nucleus. Your atomic radii is going to decrease, and then again, your ionization energy is increasing, as well as your electron affinity. Okay, so because you have this greater pull on the electrons, everything it's going to be harder to take away electrons. And those are the periodic trends. And that's the end of chapter 4.